You have to understand something. This is a real puzzle. When you look at electrons, every single one of them is absolutely identical. Same mass, same charge, same everything. You can't tell one electron from another. It's not like people or cars or anything else in our experience. You and I, we're different. Every snowflake is different. But electrons, they're all the same, exactly the same. So I said to him, why? Why are they all the same? And Wheeler says to me, because they are all the same electron. Now think about that for a second. All the same electron. There's something like 10 to the 80th power electrons in the universe. That's a 1 with 80 zeros after it. That's more electrons than there are grains of sand on all the beaches on Earth, more than there are stars in all the galaxies we can see. And Wheeler's telling me they're all the same electron, the same one? How could that possibly work? Well, let me explain what Wheeler had in mind, and it's really quite beautiful if you think about it in the right way. You see, we physicists, we like to draw diagrams of what particles are doing. We draw what we call world lines. Imagine you're walking down the street. If I made a movie of you and stacked up all the frames, one on top of the other, I'd get a line showing where you were at each moment in time. That's your world line through space-time. Time goes up, space goes sideways, and your world line traces out your path. Now, an electron has a world line too. It moves through space, and as time goes forward, it traces out this line. Normally, we think there are billions and billions of these world lines, one for each electron in the universe, all going forward in time, never touching, never crossing in funny ways. But Wheeler, he had a different picture. He said, what if there's just one world line, one electron? But this world line, instead of being a simple line going forward in time, is like a huge, enormous, incredibly tangled knot. It goes forward in time, then it loops around and comes back. Then it goes forward again, then back again, zigzagging through time and space in this incredibly complicated way. Now here's the beautiful part. Imagine you take a slice through space-time at one moment in time. Today, let's say, Monday. You take your knife and you slice through this enormous tangled knot of world line. How many times does your knife hit the line? Many, many times. Each place where the knife cuts the line, that's an electron. That's where the electron is, at that moment in time. So at this particular moment, there could be billions of intersections with this one world line, and each intersection looks like a separate electron, but it's really all the same electron, just at different points along its incredibly tangled journey through time. Now you might say, wait a minute, Feynman, if the electron is going forward in time in some places and backward in time in other places, shouldn't we be able to tell the difference? And that's the really clever part. When the electron is moving forward in time, it looks like a normal electron. Negative charge, moving from the past to the future. But when it's moving backward in time, when it's going from the future to the past, it looks like it has a positive charge. It looks like what we call a positron, which is the antiparticle of the electron. You see, moving backward in time with a negative charge looks exactly the same as moving forward in time with a positive charge. It's like running a movie backward. If you watch an electron moving forward, and then you run the film backward, it looks like a positron moving forward. So Wheeler's idea was that electrons and positrons are the same thing. They're all this one electron, and when it's moving forward in time, we call it an electron, and when it's moving backward in time, we call it a positron. Now, I have to tell you, when Wheeler told me this, I was excited by the idea, but I immediately saw a problem. I said to him, but Professor, there aren't as many positrons as electrons. And this is true. When you look at the universe, you see way more electrons than positrons. Way, way more. If Wheeler was right, and the electron goes forward and backward equally, you'd expect to see the same number of electrons as positrons. Half the intersections would be forward in time, half would be backward. But that's not what we see. Wheeler said, well, maybe they're hidden in the protons or something. And I've got to tell you, that wasn't very convincing. But you know what? Even though the whole idea doesn't work as an explanation for why all electrons are the same, Wheeler gave me something tremendously valuable. He gave me the idea that you could represent a positron as an electron going backward in time. And that idea I stole. I took that and I used it. And it became part of my work on quantum electrodynamics. I wrote a paper in 1949 called The Theory of Positrons. And in that paper, I showed that you could describe positrons as if they were electrons with their time direction reversed. Let me explain what I mean by that, because it's really quite practical. Imagine you have an electron moving along, and it encounters a photon, a particle of light. The photon has energy. What can happen? Well, The photon can create a pair of particles, an electron and a positron. The electron moves forward in time, and the positron, we say, also moves forward in time, but it's the antiparticle. But there's another way to think about it. The photon doesn't create two particles. Instead, it makes the original electron reverse direction in time. The electron bounces off the photon and starts going backward. When it's going backward with negative charge, it looks like a positron going forward with positive charge. Later, this positron might encounter another electron and annihilate. When matter and antimatter meet, they destroy each other and turn into pure energy, into photons. But in my picture, this isn't annihilation at all. It's just the electron bouncing again, reversing its time direction again. It was going backward, hits another photon or another interaction, and starts going forward again. So you can describe all of these processes, pair creation, pair annihilation, scattering, all of it, by thinking of just electrons bouncing back and forth in time. Every time an electron goes forward in time, we call it an electron. Every time it goes backward, we call it a positron. Now, does this mean the electron is actually traveling through time? Does it mean time travel is real? Well, no, not in the way you might think. What it means is that mathematically, this is a useful way to describe what's happening. The equations work, the calculations work, and in physics, if the mathematics describes what you see in experiments, then it's a valid way of thinking about nature. In fact, this way of thinking became crucial for developing what we call Feynman diagrams. These are little pictures we draw to represent what happens when particles interact. In these diagrams, when you see a line going backward in time, it represents an antiparticle. A positron moving forward in time is drawn the same way as an electron moving backward in time. And here's something wonderful. When you use this idea, when you think about antiparticles this way, you can calculate things. You can predict what will happen in experiments. And when you do the experiments, nature agrees with the calculations. The predictions work. This tells us something deep about the symmetry of nature, about the relationship between particles and antiparticles, about the way time works in quantum mechanics. But let's come back to Wheeler's original idea. Is there really just one electron in the universe? Well, almost certainly not. We have that problem I mentioned. There are way more electrons than positrons. If it was one electron zigzagging back and forth, you'd expect them to be equal in number. And there are other problems too. Think about causality. If electrons are really moving backward in time, you might worry about cause and effect getting mixed up. Could an effect happen before its cause? Could you change the past? These are the kinds of paradoxes that make physicists uncomfortable. But you know, Wheeler knew this. He knew the idea probably wasn't literally true. He wrote later in his memoir that he was aware of the problem with the unequal numbers of electrons and positrons, at least in our corner of the universe. He said, I knew, of course, that at least in our corner of the universe, there are lots more electrons than positrons, but I still found it an exciting idea. And that's important. Sometimes in physics, an idea doesn't have to be correct to be valuable. Wheeler's idea was valuable because it made us think differently. It made us ask questions. It led to insights about antimatter and time symmetry that turned out to be useful, even if the original idea wasn't right. You see, in physics, we often use thought experiments. We imagine situations that might not be real, but that help us understand the principles. Einstein did this all the time. What if I rode on a beam of light? What if I was in an elevator accelerating through space? These aren't real situations, but they help you think through the consequences of your theories. Wheeler's one-electron universe was like that. It was a thought experiment. It was a way of asking, what if we took the symmetry between particles and antiparticles seriously? What if we took time reversal seriously? Where does that lead us? And where it led was to a deeper understanding of quantum field theory, to better ways of calculating what happens when particles interact, to the whole framework of Feynman diagrams that we still use today. Every time a physicist draws a diagram with an antiparticle in it, they're using the insight that came from Wheeler's crazy phone call. There's another interesting angle to this. The equations of physics, most of them anyway, they don't care about the direction of time. If you took a movie of electrons and positrons interacting and you ran it backward, it would look just like valid physics going forward. The equations work both ways. Nature doesn't seem to prefer one direction of time over the other, at least not at the level of individual particles. So why do we experience time going in one direction? Why do we remember the past but not the future? Why does a broken egg never reassemble itself? That's a different question, a question about entropy and the second law of thermodynamics, about the arrow of time. But at the fundamental level, at the level of individual particles, time is more symmetric than you might think. Wheeler's idea plays with that symmetry. It says, what if we take it literally? What if we really allow particles to go both directions in time? And when you do that, you find that antiparticles naturally appear in your theory. You don't have to put them in by hand. They emerge from the mathematics. Let me tell you something else that's fascinating. When I developed my approach to quantum electrodynamics, I used something called the path integral formulation. The idea is that when a particle goes from point A to point B, it doesn't take just one path. It takes every possible path. It goes straight, it zigzags, it goes backward in time, it goes faster than light, it does everything. And you add up the contributions from all these paths to get the final answer. Now, most of these paths cancel each other out. The weird ones, the ones that go backward in time or loop around in crazy ways, they mostly don't contribute, but not entirely. There's a small contribution from these strange paths, and that contribution is real and measurable. When you include it in your calculations, you get better agreement with experiments. So in a sense, particles really do explore all possibilities, including going backward in time, even if we don't see that directly. The mathematics of quantum mechanics forces you to include these possibilities, and when you do, you get the right answers. Now, could Wheeler have been right in some weird way? Could there really be just one electron doing this cosmic dance through time? Well, probably not in our observable universe, but it's fun to think about. If the universe is bigger than what we can see, if there are regions beyond our horizon, maybe the missing positrons are there. Maybe in the full universe, the numbers balance out. Or maybe, as Wheeler half-jokingly suggested, the positrons are hiding in protons somehow. We know now that's not right, but it shows you how these ideas get you thinking, get you asking questions. The important thing is this. Wheeler's idea, even though it was probably wrong as a literal description of reality, led to real progress in physics. It led to better ways of thinking about antiparticles. It led to the development of Feynman diagrams. It led to insights about time symmetry in quantum mechanics. It inspired people, made them think in new ways. And that's what great ideas do in physics. They don't all have to be correct. They have to be interesting. They have to make you think. They have to lead somewhere. Wheeler's one-electron universe did all of that. You know, when I look back on that phone call, I'm grateful to Wheeler. Not because he was right about there being one electron. He wasn't. But because he gave me a new way to think about positrons, about antiparticles, about time. He gave me a tool that I could use, that I could develop, that became part of my life's work. That's what a good teacher does. They give you ideas that stick with you, that change how you think, even if the original idea turns out to be wrong. Wheeler was a wonderful teacher, full of crazy ideas, always pushing the boundaries, always asking, what if? That's the spirit of physics. That's the spirit of discovery. So the next time you hear about electrons and positrons, about matter and antimatter, remember Wheeler's crazy idea. Remember that for a brief moment, someone imagined that every electron in the universe, all those billions and billions and billions of identical particles, might just be one electron endlessly looping through time. It's beautiful, it's wild, it's probably wrong, but it's the kind of idea that makes physics wonderful. And that's the thing about physics. We're always looking for the simplest explanation. One electron instead of billions, that would be simple. Too simple, as it turns out. But you have to try these ideas. You have to push them as far as they'll go. That's how you learn. That's how science advances. The universe is strange, stranger than we can imagine. Electrons really are all identical. Positrons really do behave like time-reversed electrons, at least mathematically. Particles really do take all possible paths through space-time. These aren't just ideas. These are facts about nature that we've confirmed through experiments again and again. So maybe there isn't just one electron in the universe, but the fact that someone could even conceive of such an idea, could work out its implications, could see where it led, that tells you something about the power of human imagination and the beauty of theoretical physics. That's what I wanted to share with you today. Not just the idea itself, but the story of how ideas work in physics, how they inspire and lead to other ideas, how even the wrong ideas can be valuable if they make you think in new ways. Wheeler gave me a gift that day on the phone, and I've carried it with me ever since. Thank you.